This material doesn't break. It doesn't disappear. And right now, as you listen to these words, it is almost certainly inside your body. It's in your blood, your liver, and your lungs. It's in the rain falling over the Himalayas and the ice sheets of Antarctica. It is a ghost in the machine of modern life, an invisible companion that will outlive your children, your grandchildren, and the very civilization that created it. We didn't invent it to be a poison. In fact, we invented it to be a savior. This is the story of how a perfect engineering solution created a global, permanent problem. In the early 20th century, the average American kitchen was a potential death trap. Before the sleek, silent refrigerators we take for granted today, keeping food cold was a dangerous game. Early refrigerators used gases like ammonia, methyl chloride, and sulfur dioxide to pull heat away from your groceries. These chemicals were effective, but they had a fatal flaw. They were either highly toxic, extremely flammable, or both. If a seal broke in the middle of the night, a family might never wake up. In one horrific incident in a Chicago hospital, a leaking refrigeration system killed over 100 people. The world had a desperate problem. We needed a miracle of engineering, a substance that could provide the benefits of modern cooling without the risk of a sudden, fiery death. In 1928, a team of engineers at General Motors and DuPont set out to find it. They were looking for the Goldilocks chemical, something stable, non-flammable, and completely non-toxic to humans. They found it in a class of chemicals we now call CFCs. But the real breakthrough came a decade later, by accident. A young chemist named Roy Plunkett was experimenting with refrigerant gases when he noticed something strange. A pressurized cylinder that should have been empty still felt heavy. He sawed it open and found a white, waxy powder that didn't behave like anything else on Earth. It was incredibly slippery. It was heat-resistant. Most importantly, it didn't react with anything. Not acid, not fire, not water. To an engineer, this was the Holy Grail. They had discovered a material that seemed to defy the laws of decay. They called it PTFE, but the world would soon know it by a different name, Teflon. It was the ultimate forever material. Because it didn't react with anything, it was seen as the safest substance ever created. If it didn't react with the environment, how could it be harmful? It was a triumph of human ingenuity. We had finally built something that couldn't be broken. But here is where the logic of engineering hits a terrifying wall. The very property that made this material a miracle is exactly what made it a disaster. In the world of chemistry, there is something called the carbon-fluorine bond. It is one of the strongest bonds in organic chemistry. It is so strong that nature has no way to break it down. Bacteria can't eat it, sunlight can't degrade it, time cannot touch it. When we created these chemicals, we didn't just solve a problem for the 1940s. We locked in a physical reality for the next 10,000 years. The engineering trade-off was simple, though we didn't realize it at the time. To gain safety in our kitchens today, we traded away the biological purity of the future. By the 1950s and 60s, these forever chemicals were being manufactured on a massive scale. They were flowing out of factory pipes and into the water. They were being sprayed onto fields and tossed into landfills. And because they are designed to never break down, they began to do something engineers call bioaccumulation. They didn't just sit in the water, they moved up the food chain. From the plankton to the fish, from the fish to the eagle, and eventually to us. The turning point didn't happen in a high-tech lab, but on a small farm in Parkersburg, West Virginia. In the late 90s, a farmer named Wilbur Tennant noticed his cattle were acting strangely. They were losing weight. Their teeth were turning black. They were becoming aggressive, almost rabid, before dying in agony. Tennant had lived on that land his whole life, and he knew something was wrong with the water. The creek that ran through his property was downstream from a massive chemical landfill. When he performed his own autopsies on the dead cows, he found internal organs that were bright neon colors. This wasn't a failure of the material. It was the material working exactly as intended. It was so stable that it could travel through a cow's system, through the soil, and through the water table without ever losing its potency. As the legal battle unfolded, a dark truth began to emerge from internal memos. They had known. As early as the 1960s, their own animal studies showed that these chemicals caused enlarged livers and birth defects. In the 1970s, they found that the material was accumulating in the blood of their own factory workers. But they made a decision. It was a cold, calculated engineering decision. The benefits of the product and the massive infrastructure built around it outweighed the theoretical risk of long-term exposure. They kept the secret for decades while the material spread. It wasn't just in the pans anymore. It was in the grease-proof lining of your popcorn bag. It was in your stain-resistant carpet. It was in the dental floss you used every morning. By the time the world woke up to the reality of PFAS, it was already too late. A study of blood banks found that it is nearly impossible to find a human blood sample today that does not contain these chemicals. Even the most remote indigenous tribes in the Amazon have these molecules in their systems. This is the hidden cost of the perfect solution. As engineers, we often focus on the immediate problem in front of us. We want the bridge to stand. We want the engine to run. We want the fridge to not explode. We treat the world as a series of isolated problems to be solved one by one. But the world is a single, interconnected system. When you introduce an indestructible element into a delicate, circular system, you haven't just solved a problem. You have fundamentally altered the system itself. We are now living in the aftermath of that alteration. We are seeing rising rates of illnesses that scientists are only beginning to link back to these invisible, forever molecules. And the most haunting part? There is no undo button. You can't filter the entire ocean. You can't vacuum the atmosphere. We have engineered ourselves into a corner. We created a material that was too good at its job. It was designed to stay, and so it stayed. This forces us to ask a difficult question about the way we build our world. Is a design truly successful if it solves a problem today, but creates a permanent one for tomorrow? We often celebrate the genius of the breakthrough, the moment the light bulb goes off and the miracle material is born. But we rarely discuss the lock-in, the moment a decision is made that cannot be reversed. Every engineering choice is a trade-off. We traded the acute, visible danger of exploding refrigerators for the slow, invisible, permanent danger of environmental contamination. We like to think of progress as a straight line moving upward, making life safer and easier with every step. But perhaps progress is more like a web. When you pull on one string to tighten it, you inevitably loosen another somewhere else. The most dangerous designs in history aren't the ones that collapsed or blew up. Those failures are loud. They are obvious. We learn from them, and we fix them. No, the truly dangerous designs are the ones that work perfectly. The ones that do exactly what we ask them to do without complaint. They sit quietly in the background of our lives, performing their miracles day after day, while slowly weaving themselves into the very fabric of our biology. Today, we're building systems even more complex than anything before. Artificial intelligence, synthetic biology, global-scale infrastructure, and each of them carries the same hidden question. What are we solving, and what are we creating in the process? Engineering doesn't just solve problems. It decides which problems we are willing to live with. The most haunting legacy of the 20th century isn't what we destroyed. It's what we built that will never, ever go away.